So the pressure for 1 and 2, it's this 3 atmospheres, or 3.039 times 10 to the 5th, 3.039 times 10 to the 5th, times delta V. The change in volume, it went from 1 to 3, yeah, so 3 minus 1 is 2. Right? So 3 minus 1 is 2. So the work is 6 something.
607,800.
Okay. 6.07 what?
878.
Okay. Times 10 to the 5th?
Yes.
Joules. Okay. I'm just trying to double check with my 6.078 times 10 to the 5th. Yeah. So 6.078 times 10 to the 5th. And I will try to keep everything written as something times 10 to the 5th throughout this table, so that it's easy to compare the numbers. Okay. Now the Q. Q is CP, yeah, constant pressure, and CP delta T. So you will have the number of moles. It's 40.3. CP is what? 7/2 R, and then delta T. From 1 to 2, the temperature went from 900 to 700, so we get a positive quantity. So let's do that. I will wait. So we got delta T will be 2,700 minus 900.
1,000.
You said what?
1,800.
Should be a little bit more, I think. Because the number of moles is 40.
Oh no, I was saying for delta T.
Oh, for delta, okay. So how about when you multiply the whole thing?
Oh. 2,127,1,2.
Okay. Let me write the n just one time, so we're on the same page. So 40.63. That's the number of moles. CP is 7/2 times R, and R is 8.31, and delta T is 2,700 minus 900, and you get. I will write it in powers of something comes 10 to the 5th, so I get 21.3 times 10 to the 5th joules. Okay, 21.3. Technically, it's 2.13 times 10 to the 6th, but I will move the decimal, so I keep everything. 21.3 times 10 to the 5th. Now, delta E thermal. How do you get the change in thermal energy?
Q minus W.
Huh?
Q minus W.
Q minus WS, yes, yeah. Or you can use the NCV delta T. But since we have these two, why not just subtract them? So 21.3 times 10 to the 5th minus 6.078 times 10 to the 5th, and you get the delta thermal is Q minus WS, and it turns out to be 15.2 times 10 to the 5th. So 15.2 times 10 to the 5. So that is that. Okay, so, and then we have to do from 2 to 3 now. From 2 to 3. From 2 to 3, we said it's isochoric. So WS is equal to 0, and that means delta E thermal is just equal to Q, right? Because the W part is 0, so this and this are equal. Now it's isochoric, so NCV delta T. Yes.
So in this problem for CP we used 7/2, but in the last problem we used 5/2.
Yeah.
Why is that?
Yeah, so for this one, it was monatomic. Yeah. And this one is diatomic.
Okay.
Yeah. Good question, yeah. So, let's get, this one, so delta E thermal and Q are the same, so it's N CV delta T. CV is 5/2 R, right? So let's multiply them. So in this case, from 2 to 3, the temperature dropped. So you went from 2700 to 900. So it'd be this minus this. Fine. So it'd be negative. I mean, earlier we went from 900 to 2700, and now we're kind of going reverse. So it would be the same value for delta E, but with a minus sign, right? It would be minus 15.2.
Yes.
So you got minus 15.2 times 10 to the 5th joules. So minus 15.2 times 10 to the 5th joules. And the same thing for Q because they're equal. Here's 15.2. And then let's do 3 and 4 quickly. 3 to 4, 4 to 1. So from 3 to 4, we're repeating what we did from 1 to 2. 3 to 4. So 3 to 4, it's isobaric. So WS equals P times delta V. And the pressure is from 3 to 4. The pressure is 1.013 times 10 to the 5th. And then delta V was from 3 to 4. Would be 1 minus 3?
Oh, it's
So
1
negative
minus
2?
3.
So 1 minus 3. Right? The volume at 4 is 1 cubic meter according to the graph.
Right.
And the volume at 3 is 3. So be negative in this one. So I have minus 2.03 times 10 to the 5th joules. So let's write this here. Minus 2.03 times 10 to the 5th. Okay. And then for the Q part, Q is NC PV. Which one? P, constant pressure. And CP, delta T. So is it going to be positive or negative now for CP, for Q? What happened to the pressure? At 3 versus 4, or 4 versus 3? Dropped, right? Went from 900 to 300, right? It was 900 and 3 became 300. So Q will be negative, right? It will be minus. So let's calculate that. And again, just for the sake of time. So N is 40.63, CP is 7/2 R, and delta T would be 300 minus 900, so it'll be negative. So multiply them together, and that should give you minus 7.08 times 10 to the 5th. Minus 7.08 10 to the 5th joules. And so delta E thermal Q times WS. So this minus this. So when you do minus, make sure you include this also minus. So it'll be minus minus. So we look like this. Right? Okay. So it'll be minus 5 something. Minus 5.06. Minus 5.06 times 10 to the 5th. And this one is, who said minus 7.08? 7.08. So now, this one we don't really need to do. Why? What's the change in thermal energy over the entire cycle?
0.
0, because you come back to the same point. So that's the same temperature, so the thermal energy would have to be, for the entire cycle, has to be 0. So 15.2, negative 15.2, these will cancel each other, so that's 0. This one is negative, so I need another positive here to cancel it for the entire cycle. So no need to do another calculation, because if you do the calculation, you get exactly that. 5.06 times 10 to the 5th. Now, since the work is 0, then delta E thermal, which is Q minus W, but W is 0, so delta E thermal is equal to Q, so Q would be what?
5.06.
5. So you can save yourself a little bit of time. What's the total work for the entire cycle? The net work or the total work?
4 point something.
Yeah, 4 point something. So let me write it here. 4.05. Yeah. I will just round. 4.05. So now the efficiency is what? The work that you get divided by the heat that you put in. Now, the work you got is 4.05 times 10 to the 5th. Now, how much heat did we put in? How much heat flowed into the system?
21.3.
Plus.
This one and this one, both are positive.
Alright.
Yeah, those are the heats that came into the system. So 21 and 5, that's 26 something. So this and this, 21.3 plus 5.06. Apparently it is
26.36.
how much was it? 26.36 times 10 to the 5th. And so let me write it here. QH is 26.36 10 to the 5th. So when we do this, well, 10 to the 5th, 10 to the 5th cancel. How much is that? 15%?
Yeah.
Yeah. 0.15, which is 15%. Now, how much is QC, by the way? What is Q cold? How much heat exited the system?
15.2 plus 7.08.
The sum of these two negatives. That's the heat that has exited the system. So how much is it? 15 and 7 is 22 something, right? So it would be the absolute value of, let me just write down that. 22.3? Negative 22.3 times 10 to the 5th. So that's 22.3 times 10 to the 5th joules. So here's what's happening. Here's the hot reservoir, pH, and here's cold, and so you have heat flowing in. It gives you work, and then so this is QH, and this is QC. So QC gets to the cold reservoir. This one flows from the hot. So QH is equal to W plus QC. In other words, W is equal to QH minus QC. And does it add up that way? Yes, because 26 something minus 22 something is 4 something. So yeah. Okay, so I think these are two good problems. We can easily spend another 2 or 3 weeks in thermodynamics, but we don't want to do that. We'll do it at the expense of electrodynamics. So we're going to get to electromagnetism. So I want to do one more theoretical problem, which is about Kernel engines and the efficiency, the maximum efficiency. So let's recall what the second law of thermodynamics said, and then maybe I will erase the board and then. I'll try to be as detailed as I can. I think the book's discussion is pretty good, but it kind of gives you bits and pieces, but nothing, not in one place exactly what it is. So for the second law, we said delta S, the change in entropy is always greater or equal to zero, always, for the universe. Let's say here's the universe. Universe will consist of the system plus the surroundings, right? The system plus everything around it. So what's the universe? For example, it's me plus everybody else. Okay, so delta E, delta S for the system plus delta S for its environment. That's greater or equal to zero. Now, if the process is reversible, you get the equality. It's equal to zero. So this is, you get, when is it equal to zero? If it's reversible. If the process is irreversible, then it is with the greater sign. I'll try to explain why. If it's equal to zero, if you get the equality, the change in entropy is equal to zero, and I reverse it, well, it will stay equal to zero, right? The negative of zero is zero. However, if it's greater than zero, and I go back in time, it means the entropy is decreasing, which is not allowed. Therefore, it's irreversible. Does that make sense? Okay, good. So that's one thing we want to get. Next, we want to apply this to a heat engine. A heat engine is surrounded by two things. Well, itself. So for the heat engine, you have the system, which is the heat engine. So let's apply it to heat engines. So you have this delta S universe equal to delta S for the system, which is the heat engine. Now, what is surrounding the heat engine? Everything else. So the heat engine lives between two reservoirs, a hot one and a cold one. So the change in entropy in the hot reservoir plus the change in entropy in the cold reservoir. Okay. The cold reservoir usually is just the environment. If it's your car running, the exhaust. That's the heat exiting to the environment. So delta S for the C for cold reservoir plus delta S for the hot reservoir. And this has to be greater or equal to zero, isn't it? Right? So over a cycle, let's analyze this. We want to check what the change in entropy over an entire cycle is. Over one cycle, when we go in a cycle, the pressure goes back to what it is, right? Right? If you go for a cycle from 1 to 2, 2 to 3, 3 to 4, and then 4 back to 1, the temperature goes back to what it was, the pressure is back to what it was, the volume is back to what it was, all the state variables go back to what they were. The same thing with entropy, it goes back to what it was, it's a state variable. So that if the entropy goes back to what it was over a cycle, then what is the change in entropy for the system? Zero. Yes, good. So in one cycle, let's look at here. So I got zero for system, so zero, plus the change in entropy over the cold. So let me drop the zero. So delta S for the cold reservoir plus delta S for the hot reservoir greater or equal to zero, right? Now, what is the entropy? How did we define it for a slow quasi-static process? What did we say? ds equals to what?
dq over t.
Huh?
dq over t.
dq over t. Good. Now, a hot reservoir, by definition, the temperature does not change. A cold reservoir, the temperature does not change. So for both of them, you're changing the entropy at a constant temperature. So the temperature of the hot reservoir stays the same, and the temperature of the cold reservoir stays the same, right? Remember what a reservoir was? some big body that has one label, which is, this is my temperature. And that temperature, it's so big that its temperature does not change, essentially. So if it's isothermal, and I integrate, the 1 over T comes out, so I integrate, I just get Q. So delta S for an isothermal process is just Q over T. Okay, Q over T. So let's look at the cold reservoir. What did we do to the cold reservoir? Did we add heat to it or take away heat from it?
You added.
We added. So the change in entropy for it is positive. So it's Q cold, we added QC right to it at a temperature TC. The temperature of the cold reservoir is TC. What did we do to the hot reservoir?
Took away.
We withdrew some heat from it. Right? We took heat. Where did heat come from? It came from the hot reservoir. So if we took heat away from it, so that means we took heat. So that there, hence the minus sign. So QH over TH greater or equal to 0. Okay? This is general. I have not said whether it's reversible or irreversible. We will consider both cases in a moment. Okay? So now let's move this to the other side so I get this. I'm going to take this expression and do some algebra with it. So I get this. QC over TC is greater or equal to QH over TH, right? Let's now divide by QH and multiply by TC on both sides. So I get QC over QH is greater than or equal to TC over TH. Are we in agreement so far? Okay. Yeah.
Can you just repeat that over? Can you just like show what you did?
From here to here? Or
One more step.
for this one?
Yeah.
So I moved this to the other side. Look at this.
Why is there a minus though?
Oh, I said the change in entropy is the heat over the temperature, right? If it's an isothermal process. If you add heat, then Q is positive.
Yeah.
If you take away heat, then it's negative. We added heat to the cold reservoir, but we took away heat from the hot reservoir.
Oh, okay.
So that's why there is one. So we moved it to the other side. And so now I'm going to multiply both sides by -1. If it's mathematically acceptable, please agree with me. What should I put here to the inequality if I multiply both sides by -1?
Change the sign.
The inequality flips. Yes, when you multiply by -1, inequality flips. Yes. I mean, 7 is more than 5, but -7 is less than -5. So now I'm going to add 1 to both sides. So I have 1 minus QC over QH is less or equal to 1 minus TC over TH. Okay? Now what is this? That's the thermal efficiency for any engine. So this is the eta, the thermal efficiency. So it says the thermal efficiency is always less or equal to 1 minus TC over TH. If you have a reversible engine, you will have the equality. If you have an irreversible engine, you will have less than. So the thermal efficiency for a reversible engine is always greater than an irreversible engine. Okay? And all reversible engines, furthermore, they have the same efficiency. Okay? So, does this make sense? There's a little.
Can you repeat what you said just
Yeah.
right now?
So this is by definition, it is the thermal efficiency. Because, let me put it here. Remember, eta was equal to the work out, right? Divided by QH. And the work out was the difference between QH and QC. It was QH minus QC divided by QH. And QH divided by QH is 1.
Oh, yeah.
So that's the thermal efficiency for any engine. And it says the thermal efficiency, which is this one, is always less than or equal to 1 minus the temperature of the cold reservoir divided by the temperature of the hot reservoir. And then we said, this is for any engine. If it's reversible, then you have the equal sign. If it's irreversible, then you have the inequality. It's always less than or equal. All right, so that's that. So that's something I felt most books, they don't spell out. So now, what do I have to do to maximize the efficiency? If I have a reversible engine, it would be equal. So what should you do to this to make the efficiency as large as possible?
Make the T as small as possible.
The largest efficiency would be 100%, right?
Right.
Yeah.
Largest efficiency would be 1. 1 is 100%. So I need to make this thing as small as possible. So I can make the temperature as low as possible and pH as high as possible. Now first of all, a car engine, if you're doing a car engine, TH, you can't go beyond the melting point of steel, right? Otherwise your engine will melt. And everything else probably around it. And TC, you're limited, you can't go below, this is usually the environment, pretty much. It's room temperature, essentially. Okay, so there's a maximum efficiency. You can't build an engine that's more efficient, that has a higher efficiency than this. You're limited. And now if you add friction to it, only makes things worse. Okay? Yeah. So now how do we construct this engine? And what is it? So an engine that has the most efficient engine, let me write it for the reversible. I'm going to write this one. It's called the Kernel Engine. Let's see if we can do it in 20 minutes. So I have this. For any engine, I have eta is less or equal to 1 minus Tc over Th. And then if it's reversible, I would have 1 minus Tc over Th. Now if I create an engine that runs on a gas, let's say an ideal gas, and the efficiency turns out to be this, then I know I have made that, I hit the maximum efficiency. So how do I build it? Well, by luck, pretty much. Not really. You have to use isothermal and adiabatic processes. So here's how the Kernel engine looks like. Okay. Yeah, that's okay. We'll work here and there. So here's V. V on the x-axis, yes. And here's P. You have two isotherms. Here's an isothermal curve, and here is another isothermal curve. Okay, this is because it's isothermal. Which curve has the higher temperature? The higher curve. Yeah. So this one, let's call it T high, and this one will be T low. T actually cold. And again, these are two isotherms, right? Let's draw two adiabats, maybe with a different color. So let's say I'm here. What did we say an adiabat looks like? Is it
Like
steeper? Even steeper. Yeah, so it looks like this. This is an adiabat. And here is another adiabat. So our engine will run through this cycle. Here is, you can label this as 1, this as 2, this as 3, and this as 4. And that's your cycle. The question is, given this engine, what is the efficiency? What's the efficiency of this engine? The efficiency will be, first of all, this is adiabatic, so what's the heat? Zero. What's the heat here? Zero. Heat, this is the higher temperature, so heat would be transformed in this, and then heat will exit here. So I only have heat transfer between these two, between 3 and 4 and 1 and 2, and then everything else, there is no heat. Okay? So let me write it here. So, and I actually don't need. Can I erase this one? It's kind of coming over
Yeah.
there. Okay. So I have this. In general, by definition, the efficiency is 1 minus QC over Q hat. Q hat. So let me calculate the heat Q from 1 to 2. Q from 2 to 3 is 0 because it's adiabatic, and Q from 4 to 1 is 0 because it's adiabatic. So there is only heat here and heat here. So let me calculate from 1 to 2. What is the heat? So from 1 to 2. The heat, it's an isothermal process. So I know that delta E thermal, which is equal to Q minus WS, right, is equal to 0 because they are, the temperature doesn't change in an isothermal process, and therefore Q is equal to WS. And along an isothermal curve, the work done is NR what? NRT natural log of what?
Volume final or volume.
Good. So NRT, which T? Here. What is the temperature here? Is it cold or hot?
Cold.
Cold. Yeah. And then ln of the final volume over the initial volume. The final volume would be the volume at 2, the volume at 1. V2 over V1. Is this going to be a positive number or a negative number? This is positive, positive, positive. So it boils down to V2 over V1.
It's negative.
V2 is less than V1, so this is a less than 1 number. Natural log, if it's less than 1, you get negative. So it's a negative number. So I'm going to write it this way. So Q here will equal to negative NR TC ln of V1 over V2. I mean, if I flip this one, it's like raising it to the power minus 1. So this is mathematically correct. Okay, so just some algebra there. Yeah.
Why would you write it that way?
Why would I write it that way?
Yeah. Why can't you just write it in the normal way?
On purpose, because there is a step in the fusion.
Okay.
So, so this heat, so you see now, V1 is greater than V2. So this is a positive number, but there is an overall minus sign. So this is heat that leaves the system. So this is QC. QC will technically be the absolute value of this. Okay, so let me write it. So QC will equal to just the absolute value of that. So it's just nRT ln of equal ln of V1 over V2. So, and I'm sure that this is a positive quantity because V1 is larger than V2. And then from 2 to 3, we said Q is 0, right? Because it's adiabatic. And then from 3 to 4, isothermal expansion. Isothermal expansion, right? From 3 to 4, it's expanding. So, delta E thermal again is equal to 0, which is Q minus WS. So Q is equal to WS, and WS is nRT what? Hot. Yes. And then ln of V final over V initial, isn't it? V final over V initial. The final is 4, and the initial is 3. So V4 over V3. And this is a positive quantity, right? Because V4 over V3 is more than 1. So this is QH. This is the heat that enters the system, is added to the system. Therefore, the efficiency will be 1 minus QC over Q hot. And so that's equal to 1 minus, QC is NR TC ln of V1 over V2, and then NR T hot ln of V4 over V3. I just substituted QHs and QCs. Now, huh?
The negative.
Which negative? QC is just that.
Oh, you put that, okay.
Yeah, it's the, QC is just the absolute value of this. Yeah. So, by the way, N and R, they cancel. So I would have the maximum efficiency would be 1 minus TC over TH, but there's these two annoying logs that need to cancel. They have to somehow go away. And they will go away, so let's make them go away. So V1 over V2 has to equal to V3 over V4. That's the idea. So how do I do that? So I will write here. That's probably the last step, last thing I will do. Now, how do I show that V1 over V2 is the same as V4 over V3? Well, let's see. Let's go from 2 to 3. Those are adiabats, right? They're connected. Those are adiabats. So from 2 to 3, it's adiabatic. So you remember for adiabatic, it's P2 V2 to the gamma will equal to P3 V3 to the gamma. Yeah. For adiabatic process. Okay. So now, let me eliminate the P's. So I get this. P2 will be nRT2 divided by V2. That's P2. So it's nRT2 over V2 and then V2 to the gamma. But what is T2? It's T cold, yeah. Anywhere along this curve, it is the same temperature. So it's CC here, it's TC there. So it's TC. And then on the right side here, I have a similar thing. So P3 will be nRT3, but T3 is here, it's along that curve, so it's T hot divided by V. This is the right side, yeah. So V3 and then V3 to the gamma. So you can cancel the NR on both sides, and you end up with this. TC, and then V2 to the gamma over V2 would be V2 to what power?
Minus 1.
Yeah, to the gamma minus 1, yeah. And then here, you will have TH, and then V3 to the gamma over V3 would be V3 to the gamma minus 1. And I'm going to do the same thing for the other step. Yeah, let me do the same thing for the other step. So for step, this other idea, but from 4 to 1. 4 to 1. What's the difference between 4 to 1 and 2 to 3? What changes?
Temperature is different, like opposite.
Temperature, yeah. So how can I do it by analogy with this one?
So THV4.
THV4 to the gamma minus 1. And this one will be
TCV1.
V1 to the gamma minus 1, right?
Yeah.
So I'm using, again, the same, like, it would look like this. P4, V4 to the gamma is equal to P1, V1 to the gamma.